Yeah, dear students, I'm sharing my screen and we'll start our class. I hope you can able to see the shared screen also uh, hear me. Am I audible to all of you?
Okay.
Yeah.
Yes, sir.
Yeah, now we'll see that in the last class, we have looked at the diffraction, that is bending of light at two slits, because we have already seen the bending of light at one slit. Now I have two slits. What happens to the intensity is in double slit is that because of single slit, the single slit diffraction pattern remains as it is, as we have shown here. But in addition to that effect, because we have two slits, it acts as a double slit, Young's double slit experiment and gives you interference of equal bright and dark fringes. Therefore, these two superpose which on each other to give the resultant one, and therefore, if this is the envelope. Pink color is the envelope of diffraction. Within this envelope of diffraction, we have varying interference fringes. Therefore, the resultant contains both single slit diffraction pattern and also interference distribution. Hence, it is slightly different from the single slit. Now, what happens if I have two slits, three slits, or maybe in general n slits? So we will derive now an expression for the intensity pattern, and we also derive expressions for maxima minima conditions in n slit. Before that, we will look at what is actually a diffraction grating. So in this class, we start with by defining what is a diffraction grating and how to get this. So in the earlier classes, we looked at only one opening or one slit, or you can show the slits like this also. A slit is a opening, okay? If I say a small opening, this is the opening through which light will come. But this opening is too large for us, okay, because light will not bend, because we know that if the slit is smaller and smaller, the dimensions will approach the wavelength of the light, then only the light bends. Therefore, this is one opening. Light can come through this. And that is nothing but this is the one opening. But later we have seen as a double slit also. This is a single slit. And later we have seen that this is one slit opening and this is another opening. We call it as a double slit. Okay, where we have one opening and another opening like this, two openings. Now I will see many openings. Many openings means suppose say we have this is the slit and I keep another slit here and I keep one more slit here or many slits like this. Okay. So thereby I suppose that light can come through this. Okay. So I suppose here that light will be passed through this, okay, or through this, or through this, because this is an opening. But these lines are, okay, opaque, therefore light cannot come like this. Therefore, if I draw a pattern something like this, suppose say we have here a opening, okay, suppose say this is a closing, light cannot come. This is another closing, but between these two, light can pass through it. So I have another closing, another opening, another closing, and likewise, I have so many openings and closings. So light, wherever it is passing through the opening, this is called opening. Okay, this we call it as open, where it is a transparent for the light to come. But if I say this one, this line, whatever the line I have drawn here, this line is a closing. Closing means it is opaque, therefore light cannot come. But this opening means it is transparent for the light to come. Transparent. Okay. Therefore, here I have many number of closings, openings, closings, openings, closing, opening for the light. So thereby, if these openings and closings are so close to each other in such a way that they, okay, openings and closings are just uh, in the order of the wavelength incident on it, then light bends. So bending will take place. Similarly, what I'm supposing here is that, okay, I now define diffraction grating. Diffraction grating. So from the above, diffraction grating. So from the above discussion, we know that diffraction grating is simply an arrangement of large number of openings and closings. How many? Very, very large. That's what we have seen while doing the experiment, either lasers or you have done diffraction grating experiment to find the wavelength of light spectral lines. Therefore, diffraction grating is simply an arrangement, okay, arrangement of very large number, very large number of openings and closings, opening and closings. Okay, we opening and closings, we call it as slits. So these are slits. So I have a slit here, okay, it's open, and we have another slit here, another slit here, another slit here, but they are very, very close to each other. These are openings and these are closings. So diffraction grating is an arrangement of very large number of openings and closings, a very large number of slits. Okay, and they must be very, very fine, and they must be very, okay, narrow. So therefore is an arrangement of very large number of openings and closings which are closely spaced, closely spaced. So then how to make a grating? How to make a grating is, in general, the gratings whatever you have used in the lab consists of, they take a plain glass plate, okay, they take a plain glass plate, very, very plain glass plate like this. On the plain glass plate, okay, so to make a grating on a plain glass plate, very plain glass plate, take a okay, diamond cutter. Diamond cutter is the cutter that are used to cut glasses. You might have seen that in houses or buildings, the window glasses are cut by a fine cutter called diamond cutter. And if you cut with that, you can sharply make an impression on the glass. And then if you bend it, it exactly breaks into two parts along the line drawn by the diamond cutter. So that we call it as a diamond cutter. So therefore, on a plain glass plate, with the with the help of a diamond cutter, large number of lines are drawn. Large number of lines are drawn. So we have to draw a large number of lines with the help of a diamond cutter. Suppose I am now taking a diamond cutter here, very fine, and I draw large number of closely spaced lines, maybe one, two, three, many lines I'll draw like this. Okay, so many closely spaced lines. Here I'll draw like this. Okay, many closely spaced lines or parallel lines. So I say here is arrangement of very large number of. I can add here one more extra word to show that number of parallel openings. Parallel, I'll say parallel openings. Maybe equispaced also. Sometimes it is equispaced. Okay. So on a plain glass plate with the help of a diamond cutter, okay, number of lines are drawn like this. But you know that if you take any glass plate like this, if you make a scar on it with the help of a blade, these scars will become opaque. You might have observed it. When you're using a table, a glass, on the table glass, if you use a cutter or a sharp edge and if you draw it a line, that will become opaque. Therefore, the lines drawn, okay, by the diamond cutter become opaque. Lines drawn, whatever the lines you are drawn by diamond cutter will become will be opaque. That means light cannot come. So this become opaque. But the spacing between the lines is transparent. Spacing, okay, between the lines is transparent. So therefore, what happens is that the light can pass through it. Therefore, I have alternate openings and closings. Drawn lines are very closely spaced, and the drawn lines will be acting as a closing for the light. Light cannot come through this out, but light can come through this. Therefore, if I now take that light can pass through these openings light can pass, but these closings light cannot come through this. Therefore, I have alternate openings and closings, and there are many openings and closings. And this arrangement is called diffraction grating. So diffraction gratings are made by drawing large number of closely spaced lines with the help of a diamond cutter. The diamond cutter lines drawn will become opaque, and therefore it is acts as a closing through which light cannot come. But the spacing between the two lines is transparent, and therefore the light can come. Therefore, the spacing between any two subsequent or okay, drawings of diamond pointer act as slits. So the diffraction grating is simply arrangement of large number of openings and closings. And these large number of openings and closings are very large, okay, very large, because they should be the slit should be having dimensions in the order of incident wavelength so that light can bend. Some of you have done experiments by laser and also diffraction grating. So those who have done diffraction grating, you have noted down the value of n, capital N, which you call it as number of lines per inch, which is given by the manufacturer. Those who have done lasers also, you have noted down the capital N to calculate lambda of it. Anyone, those who have done laser, how many lines are there on the grating given to it? Did you observe it? Or those who have done
Two,
experiment of, yeah, how many?
2000.
2000 lines per inch. So you have to convert divided by 2.54. So this many lines, very huge number of lines are there on it. Therefore, that is a grating. Those who have done grating experiment, okay, this is for laser experiment, you have seen it. Those who have done grating, diffraction grating element, how many there?
15,000 divided by
Yes,
2.54.
very good. It is 15,000 lines, too heavy, very large. Okay, this is in okay an experiment called diffraction grating experiment. Why you have taken two? Why should I take different values of this in doing the laser experiment and diffraction grating experiment is important. So therefore, you have to remember that you require different number of lines or openings and closings on the grating for doing different experiments to take readings. That's we'll discuss after why I'm taking different values like this after deriving the condition for maxima minima of a diffraction grating. So now we know what is a diffraction grating. Now I'll start discussing the diffraction grating maxima minima conditions. So we know what is a diffraction grating here. Hence, diffraction grating is an arrangement of large number of parallel openings and closings or simply large number of slits. Okay, slit will have openings and closings, light will be allowed or stopped. But these are in the dimensions of these lines or openings and closings are in the order of wavelength of the incident light. Now we start deriving expression for maxima minima due to a diffraction grating. So here I'm just stopping my video and you can see the derivation what I'm doing here. Okay. So the derivation is important and will also solve some problems based on this later maybe. So to derive this, I have to draw the figure first. So we know that, okay, we have so many openings, closings, openings, closings, opening, closings like this. So this is a closing, this is the opening, this is the closing, this is the opening, this is the closing, this is the opening. Therefore, I say we have a parallel slits. Instead of parallel slits, I'm taking that slit as a vertical mode. That means we see we now derive condition for maxima and minima intensities. Conditions for maxima and minima, minima, okay, of a grating, of a grating. We have already done this for single slit, double slit, and I'll go direct. And this for the condition for maxima and minima of a grating. So to do it, we have to draw the figure. Figures are always important and you have to draw the figures when you're deriving this one. So I take a monochromatic source like this and I suppose say this is the source, monochromatic source, and we have the lines coming, the light is coming something like this. And we are in Fraunhofer diffraction. In Fraunhofer direction, we use lenses and they are at finite distance, whereas in infinite distance to make the source and the grating to infinite distance, we require the lenses. So now I keep here a lens here to make the incident light a parallel beam. A parallel beam of light is to made to fall on a grating element. That's what now we call it as a grating here. So the light is coming. Now I keep a grating at some distance. So I'm taking grating somewhere here. So the grating which I am using is having large number of one opening, closing, opening, closing, opening, closing, opening, closing. I have so many openings and closings. This is N slits, I call it as. And N slits, parallel slits, we just call this as a diffraction plane transmission grating. This is the grating. Now I keep a screen at certain distance to catch the diffraction pattern. This is the screen. And if I now take undeviated beam goes away straight and comes here and gives you a bright fringe here. Okay, but I am not interested in this, but my interest is to see the diffracted beam. So diffracted beam will have a bending, so therefore light falls on it, and I'll get a parallel light beam of light from here and it goes undeviated and I'll get a deviate a beam and the slit is illuminated. When the slit is illuminated, we know that the light now takes a diffraction or a deviation, and that deviation I'm showing something like this. When they fall on the slit, because the slit openings and closings are so small, they are comparable with the wavelength of the light, they undergo a diffraction, and instead of going straight away something like this, okay, so they will undergo a diffraction by an angle. So therefore, it will undergo a change, and to get this, I need to keep another lens in between these two so that the diffraction, diffracted light at a different angles by angle theta, they will be focused to one point. So this will get diffracted, and diffracted light, okay, bends and goes here, making an angle theta. We call it as the angle of diffraction. This also gets bent by an angle theta, and this also gets bended by an angle theta when compared to this line. And thereby the lens bends it, okay, because it's moving, bends it, and it bends here. And here the point P may be, this is 0 bright, this may be bright or dark depending on the path difference of the waves that are reaching here. I call this as A, and this we call it as B, and we have n number of slits here. And here I'm supposing that E is the slit width, that is opening. Slit width means opening. D is, okay, separation between the separation between the slits. And we call E plus D, whatever we have seen in the earlier class as for double uh, okay, slit or two slits, E plus D is the opening and closing. And this is here called as grating element. We call it as grating element. E plus D is called grating element. Lambda is wavelength of incident light. Here is monochromatic source of incident light. Incident light. Okay. These are the things what I want to know. Now, I would like to calculate the path difference and convert this into phase difference. So, as I supposed in the earlier class, same thing I have taken. In double slit, we have taken the path difference. Now, I want to calculate the path difference, path difference between any two successive slits, successive slits, successive slits I have to take. Because we have already seen in successive slits the path difference as BC, and we have written that a path difference, okay, is a path difference is BC in double slit. What we have seen, the same thing I am saying. So this I can write from, okay, the value of sine theta earlier. We have write sine theta is equal to BC by AB, where AB is nothing plus E by E plus D. So the value of that, okay, if you just remember this, what we have derived for the previous one, okay, this is the one previous one. We have derived for double slit as E plus D is thus, okay, and thereby we have drawn here, if you see this, okay, we have got it like this. BC is equal to sin theta is equal to this for double slit. So same slit I am using here, same equations also I am using here is this. Therefore, from this I now can write, okay, these values as the path difference BC is this. Therefore, E plus D sin theta, if I take here, okay, is equal to, I'll get E plus sin theta is equal to BC, the path difference. But I would like to convert into phase difference. To go to phase difference, okay, I'll see what is the phase difference. I call this phase difference as delta here, or okay, phi also you can use it. Phase difference, if I want to write, is equal to delta or phi, whatever you want, you can use it here. So that is equal to 2 pi by lambda into BC. So I get here delta is equal to 2 pi by lambda into BC. BC is E plus D sine theta is the one. And I will now write this as something like this. E plus D is the grating element, lambda is the angle of wavelength incident on it, and then I will write this one, okay, delta, as I'll take now delta by 2, which I call it as beta. So I take this to other side. Thereby, I will get delta by 2. Or I write it as pi by lambda e plus d sine theta I'll get. Therefore, here beta is now the path difference. I'll write it as pi by lambda into e plus d sine theta. Okay, and I call as equation number 1. Yeah, did you follow this? You know already? Now, how to derive the derivation? To derive the derivation, we have already supposed that while doing a derivation for single slit, we supposed that first we have taken a single slit like this and we divide it into small number of parts. But here, each part is a slit now, that is n slit. Therefore, for a single slit, if you take for a single slit, the amplitude, the resultant amplitude, we have already derived. Resultant amplitude, we derived it and we have written that for A theta for a given angle of incidence is equal to AM maximum intensity into sine alpha by alpha is the derivation what we have derived for single slit. Okay, this is single slit resultant amplitude is this. So therefore, if you apply now, I have n slits here, n openings and closings here. Each opening is a single slit. That means I have very large number of slits. I suppose n is the number of slits, and which is very large, very large. So therefore, each slit is capable of giving one single slit degree. Hence, I suppose that now from this notation, okay, I write that the resultant, resultant amplitude, I'm writing, amplitude is, okay, the combination of or resultant of combination of how many are there? N slits are there. N amplitudes each of value, each will have now amplitude AM sine alpha by alpha. Each will have this. There are n will be there. So they superpose on each other this to get the intensity on the screen. Therefore, I write the resultant amplitude R is simply equal to A into, where each A amplitude is this, A theta I can write. Each of this is this. A theta means for a given angle of diffraction. That's all. Theta into, I have sine. Okay, I will write here, there are n parts are there, suppose say in diffraction of single slit, and I write this is n, okay, delta by 2 by, I write it as sine alpha by alpha, I have to write sine delta by 2 is the resultant one. But I will write here A theta for each case is this. Since we can say that each slit will give you this amount of amplitude. Therefore, A theta can be replaced by AM. I am replacing it by AM, okay, sine alpha by alpha. That means the amplitude of each slit is this. Therefore, I am replacing it by this. Into sine, I have here n delta by 2 is nothing but beta, because we have seen here beta is delta by 2. So therefore, I write beta here. Beta by I have sine beta because delta by 2, okay, if I take it is equal to beta, delta by 2. So I'll write like this. Thereby, I write R, the resultant amplitude is equal to AM into sine alpha. This is because of every single slit into I put n. N is the number of parts which we made in the single slit. But here, instead of making that many parts, the n slits are having those many parts. Therefore, n will become capital N. So I put n equal to capital N because n number of openings and closings are there. Hence, I'll write it is sine n beta by sine beta. I will have. So this is the resultant amplitude. So I'll write resultant intensity. Resultant intensity. To get intensity, you know how to get the intensity from the amplitude? I is equal to, yeah, roll number 38. Resultant intensity I is equal to how much? So roll number 38, previous batch 2038. What is the resultant intensity? I is equal to this. From this, what is the value of I? Can anyone tell how to write I value now?
I am into sine alpha by alpha whole square.
Okay, it is I am square because I have to square it. Into, tell me, sine alpha by alpha whole square into, I have to square this.
Sine NB by sine and N beta by sine beta whole square.
Sine beta whole square. Okay, this is the resultant intensity that is coming from a grating. Okay, this is the resultant intensity we have. So you should remember this. But from this, what actually we know it? It's very simple to see it. Okay, this is consisting of two parts. This is actually the diffraction due to single slit because it is sine alpha by alpha. Therefore, we say it is a intensity distribution, okay, due to single slit. So this term is because of the effect of, okay, due to effect of single slit diffraction. And we have n single slits. Therefore, this term, we have n single slits. So this term is combined effect of n slits. Combined effect of, okay, capital N number of slits. Hence, the diffraction pattern due to a grating consists of single slit pattern as well as the combined effect of n, okay, number of slits. Therefore, we have to see how much is this. And to draw this, I will draw here to show these intensities. Later, we will calculate the condition for central maxima and right central minimum or minima expressions. I have now these two. I use it. Okay, and I'll draw here the graph. First, I'll draw graph for single slit, and then for n combination. Then resultant means the superposition of these two. We have to draw it. Therefore, first I am drawing here the, okay. So I take here the single slit diffraction. So this I am taking here, and suppose say this is, I will draw here another shape. Suppose say this I am taking. So I take here a line, and from this I draw here. This is the single slit. So to draw the single slit pattern, you know that single slit pattern will have one big envelope. So and that big envelope will have okay. So I am now drawing the envelope here. The envelope means it goes here minimum, goes to maximum at this, and comes here, and of course it is symmetrically situated. These are the minimums. Okay, and these are the minima will fall down, of course. This is the central max. So this is single slit. That means this will be due to sine alpha by alpha whole square. Of course, you can multiply by am square also. Into im also you can put. This is the one. And combined effect. What is the combined effect now? It is interference due to n number of slits, not two coherent sources. N coherent sources we have. Now, as we have n coherent sources, we will get here the interference pattern. To draw the interference pattern here, okay, I am now taking that. This is now, this is a maximum top, and I'll now draw some line from here to this, okay, so that I will show the diffraction pattern only between the central maximum, which can be repeated in secondary maximum also. So we have this. Okay, and now I will take here and I want to show and draw from here. This is the line. Okay, maximum I'm taking. Now I will have here again intensity. This is the intensity. But this intensity is due to combined effect of this. Interference pattern will have, you know, that only equal bright and dark fringes of same intensity. Therefore, here I will now take a line here so that I can draw the same height here. So therefore, here to represent this, I'm taking this color, and we have a maximum going here. Okay. So otherwise, I'll take somewhat. So we'll have a line coming like this. Look, I'll just go up and I draw here interference pattern goes maximum, comes here, okay, on either side. But we also should see that here many interference will take place. After that, it will become close, very small, and again it rises here and again falls, and we have many effects because of number of slits. Here also it becomes many, and then it goes up, increases, and here also we have many of this. These are the equal, but all of them are equal. So this is now combined effect of interference, that is sine n beta by sine beta whole square effect. This is the curve. This is the curve for this. Okay, if you see, this is the curve for this. But the real intensity, if you take it for a diffraction grating, is a product of this and this. Therefore, I have to now draw the curve for the resultant amplitude or intensity due to, okay, the entire one. So I will now draw here a line to represent this. I take a shape here. I now represent, I'll take a line here, and I would like to draw this one. So on this, I'll take here, this is the line which I'm taking at the center. Okay, center is this. Now, this is the multiplication of these two will be the resultant amplitude. So to draw that resultant amplitude, I'm using another curve, suppose say here, and this envelope, whatever the envelope that is there for single slit, this envelope remains the same here. So therefore, I'll get an envelope same like this. So if I want to draw symmetrically, okay, the envelope something goes maximum and comes here. Okay, it's not send. Okay, I start here. Sorry, and goes and falls like this. Here also we have, okay, starts here, goes here, and falls here. This is the central envelope due to sine alpha by alpha. Now within that, this has to change. Therefore, I will now show those changes, okay, within this one. That means wherever we have maximum here, this goes to maximum and this interference pattern becomes maximum here. And there are so many small ones and again it raises up as interference pattern and again it falls. But it will be there here again we have maximum, okay, coming here and we have this. That means the interference patterns or combined effect will be, okay, varying within the diffraction maximum. Therefore, within the diffraction maximum, you can show and see that there are many interference maximas, minimas. Now, this is the combination of these two. That is, it is actually I can write here Im. Okay, Im is Am square. Okay, so therefore, this will become the resultant pattern Im into sine alpha by alpha square into right sine n beta by sine beta whole square. This is the resultant part. Therefore, the diffraction pattern due to a diffraction grating consists of a central envelope of single slit within which the effect of n slits of interference will be embedded in it. We have like this. But how do I get, where do I get central maxima? This is central maxima condition. And where do I get minimas and secondary maximas? At what angle of diffraction I will get this? To derive this, we have to use the earlier conditions. To earlier condition is, so we first derive expression for central maxima. This is actually central maxima. Okay, this is central maxima. So we will now condition for first condition. Condition for central or principal maxima. Central or principal maxima. So there will be many central maximas like this. Is one central maxima. If you go for it, again I have another central maxima in this and so on. So we have to see central or principal maxima. So we will now condition for central maxima or principal maxima. To get the conditions, I will now derive simply the conditions by using Yabo equations. So we have now equation that, okay, intensity becomes maximum. We have Im, the I theta is equal to Im into sine of alpha by alpha whole square into sine of n beta by sine beta whole square is the expression for this. So we have this. Now, if you observe it, okay, intensity becomes maximum when this is 0. Sine beta is equal to 0. So when if we take it, okay, intensity becomes maximum when, okay, when sine beta is equal to 0. So if sine beta is equal to 0, it becomes 1 by 0, infinity, therefore I becomes maximum. Because if I put a sine beta is equal to 0, what are the values of this? This will become 0. But when sine beta is equal to 0, what happens? When this happens, okay, we know that when sine beta is equal to 0, okay, if sine beta is equal to 0, then, okay, sine n beta also becomes 0. Then sine n beta also will become 0. Then sine beta, okay, then also becomes 0. So if we, that is the condition, okay, if that is the condition, then sine beta n beta is equal to 0. That means if I take sine n beta is equal to 0 and sine beta is equal to 0, I'll get 0 by 0, which is indeterminate form. Determinate form. So if you have a function f of x by some expression, if that is in indeterminate form, how do you find the value of the function? Anyone? Have you applied any such laws? If you want to differentiate this, to find the value, you have seen one law called L'Hospital's law. Have you seen L'Hospital's law? Yeah. What is L'Hospital's law? Anybody?
Differentiation of numerator by differentiation of denominator.
Yes, that you have to do it. Correct, 38. So therefore, here to find maxima and minima, I use L'Hospital's rule. L'Hospital's rule. So to do L'Hospital's rule, I'll take only this part to find the L'Hospital rule, because we are keeping sine beta is equal to maximum. Therefore, I write here L'Hospital's rule, and I will write here that, okay, if I write limit of here, I suppose beta tends to plus or minus n pi. Why plus or minus n pi I'm taking? Because e plus beta is equal to 0 means that e d by sine theta lambda is equal to 0, where lambda can take 0. That means we know that, okay. Uh, so I will show how we are getting beta and pi. Simply is equal to, I'll write sine of n beta by sine beta. To find out this, I will write this as limit of beta tends to plus or minus n pi. I'll write it d by d beta of sine n beta by d beta of sine beta. How much I'll get? Anyone, can you tell me this differentiation? What is d by d beta of sine and beta? Roll number 44, roll number 15. Anyone? What is sine n beta by n beta? D by dt of this. I'll get n cos n beta by, yeah, anyone? And for d by dt sine theta is cos theta. So I'll get cos beta here. But when n pi tends to, or beta tends to n pi, what is cos n pi? Or cos, if you put n equal to 0, 1, 2, 3. So what is cos pi?
-1.
What is cos n pi?
Plus or minus.
Plus or minus 1. Therefore, this will become plus or minus 1. Hence, this value is simply equal to n. Okay, because beta is taking the value of n pi. If I put n pi value, I'll get this beta equal to n. So I'm taking positive values plus or minus n, I'll get. That means the intensity I, if I take here, you can also write that. Okay, from this I take here and write that sine n beta by sine beta, okay, when it is tending limit beta tends to a plus or minus n pi. If I take whole square of this will be simply n square, because this is n. We have seen by L'Hospital's rule that this value is capital N. From here you can see it. Therefore, the resultant intensity will be I equal to, therefore, resultant intensity, in this case, resultant intensity, I write it as resultant intensity I m into sine alpha by alpha whole square into sine n beta by sine beta is now only n square. This is the resultant intensity for central maxima. But where do I get central maxima? I supposed that the central maxima here, okay, sine beta tends to 0. That means, okay, central maxima occurs, central maxima occurs at sine beta is equal to 0. Means what should be the value of beta? Row number 59. What is the value of beta? Plus or minus n pi.
0.
So n can take 0, 1, 2, 3 and so on. Yes? Beta. So beta equal to plus or minus n pi. It will take n pi values. But what is beta? If you go for equation 1, which we have seen above, the equation 1 we have written somewhere is this. Okay, beta is equal to pi by lambda into e plus sine theta. So now I will write here beta is nothing but, okay, pi e plus d sine theta by lambda. Okay, this is the value of beta is equal to a plus or minus n pi. So if you take this, okay, and you can cancel pi on either sides. If you cancel pi, I will get the value as, okay, e plus d sine theta is equal to plus or minus n lambda. Okay, this is called, okay, grating equation. Grating equation, which we use again. Grating, we call it as grating equation. This is the condition for maximum. Okay, so it's maxima condition, or we say principal maxima conditions. There are several principal maximas here because n can take the values 0, 1, 2, 3. We have so many principal maximas. This is the condition for principal maxima. Now we have to get condition for minimum. Okay. I have to get now condition for this. So if we want to get the condition for maxima is this condition. To get condition for minima is the second one. Second one is condition for okay, minimum intensity or minimas. Because if you see here we have, okay, in this we have maximas. These are central, okay, corresponding one minimas. Here in here minimas are there, and again in between we have the secondary maximum also. Within this, okay, if you take the secondary maxima, within this again it changes like this. It changes like this. It goes and gives you like this. Therefore, I now should get condition for minimum. So the condition for minima is that we have the equation, we have the intensity I is equal to AM or IM sine of, okay, alpha by alpha whole square, okay, into sine n beta by sine beta is the condition. We have this is called intensity distribution function for grating. Intensity distribution function for grating. Now we have seen that if sine beta is equal to 0, we get maximum. But if I want to get minimum, I make sine n beta is equal to 0. Then the entire one is 0. Therefore, for minimum, okay, minima, what I suppose? I suppose sine n beta should be 0. But and sine n beta is equal to 0, sine beta also should become 0. Therefore, you have to take care that, but sine beta should not be equal to 0. Those conditions only you have to take. So to take that, if sine n beta is equal to 0, n beta should take the values of, anybody? Can you tell me what should be the values of n beta now?
Plus or minus of n pi.
Yeah, n we have already used it there. So I use another word m pi. Yes, because n we have already used here. N we have used here. So that's why we have seen sine beta is not equal to 1. Therefore, I'll write some m pi. So then I write here as n into beta. Beta is pi into e plus d sine theta, okay, by lambda is beta value. This is beta, okay, is equal to plus or minus m pi. So you can cancel pi on either side, and you can write now, okay, n into e plus d sine theta is equal to plus or minus m lambda. So thereby we now write n into e plus d, okay, e plus d sine theta is equal to plus or minus m lambda as the condition for minima intensities, where m we take the values of, yeah, what values m should take now? What are the values? M takes all integer values. Integer values. But see, if I take m equal to capital N, what happens? If I put m equal to n, what happens? Yeah, roll number 17, 28, 13, roll number 13.
Sir,
If I put m equal to capital N, what happens?
sir, M and N
Gets
cancelled.
cancelled. Therefore, it become only n lambda, that is above condition. This condition will become. Therefore, but that condition is for maxima. Minima should not come. Therefore, you should take care that, okay, or if I put m equal to 2n also, n get cancelled, 2 lambda, that 2 lambda is n lambda. And if I put 3 lambda, okay, 3n. So if I put these values, that will become a condition satisfying maxima, where I don't get minima. Therefore, m take all integer values except, okay, 0, n, 2n, 3n, and so on. In other values, it can take. If it takes the n, 2n, 3n, that will become a condition for, okay, maximum. Hence, this is the condition for minima. Condition for minima with condition of minima with this exception. And where do I get the third condition? I stop here. Secondary maxima. Secondary maxima. Secondary maxima are in between, okay, these values. So they appear between the minimas. Minima intensity positions. Minima intensity positions. Minima intensity positions. So thereby you should remember that, okay, we will get these conditions. These are the conditions for a diffraction grating. But if you see this spectrum, if I have more number of slits, then the deviation or separation becomes more and more. Therefore, some important points, two important points you have to remember is that one important point is, okay, if n is large, means number of slits are large, very large, okay. If n is large or number of slits are more, or we say number of openings or closings or number of rulings we call it as, number of slits are large, okay, then what happens? Angular spacing okay, becomes larger. What do you mean by this? I will stop within this. So this is the light coming. You have more number of slits like this. Therefore, this deviation will become more and more. Theta will become larger. As theta will become larger, you will get here one spectral line, another spectral line here, another spectral line. If I say n is small, only I take few n's, suppose say, then theta will be small. Then lines will come close to this. They'll come close. That's why we use n equal to 2000 for lasers, because we want to observe more number of lines, and the separation is small because we are using only a monochromatic light laser of red color. But if I'm using a diffraction grating, in diffraction grating, white light has several colors, and these colors should be separated largely so that we can easily recognize them. Hence, in diffraction grating experiment, n is large, which is 15,000 lines. If you keep 15,000 lines in laser experiment, then we'll get only 2 spots here and here. That's all, because the separation is larger. You don't get too many orders, and you can have only 1 or 2 measurements. But I require more measurements to calculate lambda accurately. Hence, I take less number of openings and closings, or less number of value for n. That is for laser experiment. Okay, but I want there are many white light is giving several colors, and these several colors should be separated largely so that I can see them very clearly. Hence, I should have this. That is angular separation. That means red color and yellow color should be separated for, so that I can observe it clearly. Hence, we use larger n diffraction grating in diffraction experiment and less number in laser experiment. Second important thing is higher the lambda. Okay, that means incident light, blue light, white. Okay, white light is falling. Suppose we have violet to red. Therefore, higher is the lambda. For red light, lambda is higher. Okay, higher the lambda, more the angle of diffraction. That means red light bends more in diffraction grating when it falls on it, more the diffraction angle theta, than violet light. Therefore, violet light will be the first in the spectrum, what we have observed in our diffraction grating experiment. Red light is at the corner because it is suffering large angle of diffraction since its lambda is large. Okay. So I stop here with this, and we will do some problems based on this with 2 more concepts of comparing the grating with prism. Okay. So mostly we'll have in the next class, we'll see more about grating and some important aspects and some problems in the next class. So if you have any doubts here, you can ask and clarify your doubts. Yeah, anyone having doubts? Shall I stop here?